So hi everyone, and today we are going to solve this LeetCode daily challenge. Make lexicographically smallest array by swapping elements. So you are given a zero indexed array of positive integers, nums, and a limit. And in one operation, you can choose two indices and swap nums of I and nums of j. If this condition is satisfied, like absolute difference of nums I and nums j should be less than or equal to limit. And after performing any number of operations, you need to find the lexicographically smallest array that you can form. Suppose we have this example. What we want is, like, we will consider each element one by one and we'll traverse from left to right. So like first we'll check 1. Now we want to swap 1. Okay, first thing we need to first fact that we need to talk about is that when do you want to swap. Like if our ith element is 1, we need to choose a jth element with which we are going to swap it with. Now should this jth element be greater than 1 or less than 1? First think about that. Obviously, if jth element is less than 1, then we will need to swap. See, suppose 1 is our element, and the right side of the array we found an element greater than 1. Say it is x. If we swap these two elements, then the string will become lexicographically greater. So we don't want that. We want to make it smaller. So an element greater than 1 is not a good choice. So with 1, we will always try to choose an element in the right side of the array which is less than 1. And we have a limit of 3. So with 1, what you will do, you will take 1 and you will decrease the limit from it. So 1 minus 3, we will get minus 2. Now we will check, like, if there is any element which is less than 1 but greater than or equal to minus 3 in the right side of the array. If there is such element, then we will choose that element and swap it with it, and swap it with 1. So the new string which we will obtain is lexicographically smaller. So suppose we choose 1, and in the right side of the array we will search for an element which is less than 1 but greater than or equal to minus 3. Is there an element there? See, 7, 6, 18, 2, 1. No, there is no such element. So we will let 1 as it is. Then we'll check 7. 7 minus 3, what we will find? 7 minus 3 is 4. Okay. So we will search for an element in the right side of the array which is less than 7 but greater than or equal to 4. So we have 6. So we will swap it. Now our array has become lexicographically smaller. Okay, now we will consider this 7. And see, one more thing. You don't need to consider 7. Like, you need to consider, but first you need to consider 6 again. Okay, since we were at this element, like we were at this point, right? Like when we were analyzing 7, we were at this point. We found 6 and we swap it with 6. But now there can be other element which can be present which is less than 6. 6 minus 3, that is 3. So we need to find an element which is less than 6 and greater than or equal to 3. And if we found such element, then we will swap it again. Suppose we find 4. So we'll swap it again and we'll keep 4 here. So whenever you're considering some element, you want to find the correct element which would be here, like after applying all these operations. Okay, here in this example we don't have that. We got 6 uh, and now 6 minus 3, so we need to find an element which is less than 6 and greater than or equal to 3, but we won't find that element in the right side of the array. So 6 will be the final element here. Then we will consider the third element. At this third position we will have 7. Now we'll again check, like we won't find any element, then 7 will also remain as it is. Then we'll check 18. 18 minus 3, that is also 15. We won't find any element which is less than 15, less than 18 but greater than or equal to 15. So 18 will also remain as it is. For 2, we will check 2 minus 3, that is minus 1. Now is there an element which is less than 2 but greater than or equal to minus 1? Yes, 1 is there. So here we can swap. Here 1 will come. And finally we'll check for 2. After 2 there are no elements, so we won't need to bother with it. So this is the final answer. So we will pick some element and we will find another element which is less than this picked up element and greater than or equal to picked up element minus limit. So searching that element will take O of n time. and traversing each element will also take O of n time. So this algorithm is O of n square. But like I first came up with this, then I decided to create a better approach. So I'll first code the brute force solution. So you can find the size of the array. Then you can traverse the array. Now I is the element which you are going to consider. And you will look for the jth element which is on the right side of ith element. So j will start from I plus 1. And while j is less than n, then you will check if nums of j is greater than equal to nums of I minus limit and nums of j is less than nums of I. Then we can swap. Okay, so you swap nums of I and nums of j. Okay, and after swapping, you don't want to consider the next element directly. You want to first check this ith element only first again. Okay, so because in this iteration you will most probably do j plus plus, but no, we want to start again from this ith element only. So j will again become I plus 1, and then you'll continue. And if this condition isn't met, then we'll move forward. And finally you can return nums. So this is the brute force solution. The algorithm is O of n square, so it should give time limit exceeded. Yes, it is giving time limit exceeded. Now we want to make this solution more efficient. So one thing, if you have seen in this algorithm, was that, like, if you remember when we were switching 7, when we were switching 7 here, when we were switching this, we first switched 7, then we checked for 6 again. So from 7 we were able to reach 6 using minus limit. Then from 6, if we can find another element in the right side, then we will swap it with that. Then for that element also we will search for new element which is smaller than that and greater than equal to minus limit something. So technically we are trying to find for each element the smallest element which is reachable. Okay, from 7 we reach 6, from 6 we can reach some other element. In this case it wasn't possible because 6 minus 3 is 3, and there is no element in the right side which is between 6 and 3. Okay, so that is why we cannot do it. So what can we do? What we can do is sort this array first. Okay, if I sort this array, this will become something like this: 1 1 2 6 6 7 and 18. And I'll also write the indices here, like this one is 0, this one is 5, this 2 is 4, this 6 is 2, this 7 is 1, and this 18 is 3. So these are the indices. Now check. If you add, like, you have 1, and this is an increasing order. So can you reach some element which is like greater than 1 but less than equal to 1 plus 3? So from 1 we will search 1, like 1 plus 3 will be 4. 3 is the limit here. So we need to search an element 1 to 4. 4 is included. Okay, yeah, 1 is also included. So is there any element in the right? Yes, there is. There is 1 and 2. You can reach up to 4. Okay, I mean 2 2 1 1 2. Like in this 1 in this one, if you add 3, you can go at max at 2, 4. So are there any elements which are lying in this range? Yes, there is. 1 is there which is lying between 1 and 4, and 2 is also there which is lying between 1 and 4. Then for 2 also I will check. Like from 1 I could reach 2 at max. Then for 2 as well I will check. 2 plus 3, 5. So is there any element in the right which is greater than equal to 2 and less than equal to 5? No. So from 1 you can at max reach 2. Okay. So one set you get is 1, 5, 4. From this 1 you can reach 2. Okay. Now you'll start from this 6 element. 6 plus 3 is 9. Is there any element in the right which is greater than equal to 6 and less than equal to 9? Yes, there is 7. So from 6 you can reach 7. Now for 7 as well, 7 plus 3, 10. Is there any element in the right which is greater than equal to 7 and less than equal to 10? No, there is no. So from 6 at most you could reach 7. And finally you will have 18. Okay, so what I did here is, like, from this 1 you could at most reach 2. From this 6 you can at most reach 7, and from this 18 you could at most reach 18. Now what you want to do is, like, you if these numbers are reachable, like from 1 you could reach 2, then you can swap them. Yes, basically you can swap them because it is possible for them to be swapped because they are reachable. So we will always try to create sorted array. Okay, so here 1, 1, 2 is sorted, but what you want is that their indices should be sorted as well, like 0, 4 and 5. Like, this is basically sorting. Okay, so technically in the original array what will happen, on 0th position, on 5th position, oh sorry, on this, in this original array, if I call it result, like on 0th position we have 1, on 4th position we have 2, on 5th position we have, technically we are talking about the indices in one set. In the first set we have 0, 5 and 4. So all these elements on the 0, 5 and 4 should be sorted. So consider these 0, 5 and 4, 0, 4, 5. See, the elements are 1, 2, 1. They are not sorted. So we will sort them. So 1, 1 and 2. Okay. In first set you have elements 0, 5, 4. And the elements which are present in one set, they can be swapped. And after applying all these steps, you could basically sort the array. You could draw this conclusion using bubble sort. Like, if you can swap some elements, you could always sort the array. So these elements in the same set are reachable, so these are all swappable as well. So therefore you could say that we can sort these elements. So from 0, 4, 5 you sort these elements. Then for set 2 you have indices 2 and 1. In indices 2 and 1 you need to sort these elements. These elements are not sorted. 7 and 6 are not sorted, so you will sort them. 6, 7. And finally you have 18. Since there is only one element, you don't need to sort it. So this is the answer you get through this algorithm. Now the benefit of this algorithm is that in the previous brute force algorithm you have to, like, find all the elements which lie between 1 and the limit minus 1 in WOF and temp. In sorted array you can search this using upper bound or lower bound function whose complexity is only O of log n. So this solution will be faster. So we'll code this solution. So what you can do is, first we'll create a vector of pair. Okay, and this is the vector of pair. Then you will traverse the array nums, and in the first position you will have nums of I, and in the second position you will have only the index I. With this, what you can do is, now you can sort the array by value, and you will also have indices recorded. Okay, now you can sort this. Now you want to find for each index the maximum reachable index, the maximum index that you can reach using this limit. So you have something called start. st will store the starting point of each set, and ending en will store the ending point of each index, each set. Like 0, 5, 4 was one set, and 2, 1 was one set, and 3 was one set. So the starting and ending points of those set, that is what we want to store. Now you will check if s is less than n. You will use the lower bound upper bound function, and you will traverse v dot begin, v dot end, and not v dot begin, it will be v dot begin plus s. From s element you are starting, so you will try to look in the right side of s, so from s plus 1 to end of the array, and you will search for some value. And what value is it? It is the whatever value you are choosing in the starting. So v of s dot first, this is the value. And since your vector is consist of pairs, so you need to write a comparator as well. Okay, that will write right, something like this, and this will give us a higher element. So minus v dot begin will give the position in integer, and this will return the element which is like the smallest element which is not reachable. So an element before it will be reachable. Okay, something like this. We can also define the comparator here. So you can mention the value here. This is the value which we are searching, and we are searching it inside a pair. So I could say this is, you can call it node, and you can return if value is less than node. Like by first value we are comparing, that is what we want to mention here. Okay, now after doing this, whenever you find p, you will update s by p. Okay, and it is possible that you search for an element and you don't find anything like reachable, so it will, the value of p will be equal to s at that point only. So if s is equal to p, this means that we used s but we didn't find any element in the right side. Only s is reachable with s. So this is the point that you have found one set. Okay, so you want to move s further. Here we can also note the starting and ending points. Here we will get the ending point as s only, and after this we will evaluate something, whatever you want to evaluate, and st will be, and from here when you do s plus 1, you will have a new start. Now what you want to evaluate, you remember that we get the indices and then we try to sort the values there. So that thing we are going to do here. How you will do it? You will have a vector for values and you will have a vector for indices. Okay, now you will traverse from st to end, and you will push values in this values vector, and indices vector you will push the indices. Okay, these values are already sorted, we know, but these indices are not. Okay, so we'll sort these indices. And then you can again traverse these indices, and for each indices you can update nums. Okay, so something like this will be there, or you don't need to write this, you can write simply vals, and finally you can return nums. So the time complexity for this will be O of n log n. Oh, why it is giving incorrect? Okay, sorry, we didn't write limit here, like we were searching for some limit now. Okay, so the time complexity is n log n. Okay, so thank you for watching this video. I hope you like it, and you can subscribe my channel and hit the bell icon to receive any future notifications. So thank you.